Okay, guys, in this episode, let's look at the Leetcode problem 1192. And the problem title is Find all critical connections in a network. Let me quickly go through the problem statement. The problem statement says that given an undirected graph, find all critical connections inside it. Basically, so this is a sample graph given to you. And let me just, before jump into the graph and explain you what a critical connection is, let you go through the input and output basically. So the input given to you is a value called n, which is the number of nodes, which is 4 in this case. So there are 4 nodes in this. And then you are also given a connections array. So connections array is nothing but a list of edges basically. So it's a array of edges, and you can see the edges are between 0 to 1, then 0 to 2, and 1 to 2, and 1 to 3. So basically 4 edges and 4 nodes total, right? And what you have to respond back is the output. You have to give a list of edges basically. So list of some of these edges which are actually a critical connection. Now, the next thing we need to understand is what is a critical connection. So to give you an example, let's look at this sample graph given to you. So this is the graph, and then there's the fourth node. So what is a critical connection basically? So out of these 4 edges, some of the edges could be critical connection. The best way to figure that out, whether a critical edge is a critical connection or not, is to just remove it. So if I remove this edge, does it divide the graph into 2 parts basically? And here you can see all the nodes are still connected. Hence, this connection is not a critical connection. Now, if I look at this one basically, if I remove this edge, this actually divides the graph in 2 parts. There's one part called 3, and the other part is 0, 1, 2. 3 cannot reach all the other parts. This actually ends up dividing the graph into 2 parts, and hence this particular connection is a critical connection. So that is the definition of critical connection. Let's quickly look through some of the other examples or simple examples as well. So suppose you have just 2 nodes in the system, and they're connected with a single edge. Now, is this edge a critical connection? Very simple. Just remove it. Does it divide the graph in 2 parts? Yes. Now you have 2 distinct parts which are not connected, and hence this is a critical connection. Let's look at another example. If I give you a graph like this, in this case, if you remove any of the edges, suppose I remove this edge, does it divide the graph into 2 parts? No, it does not. So this is not a critical connection. Similarly, this is not a critical connection, and this is also not a critical connection. So in this graph, there are no critical connections. Let me give you a counter example. So if you place a node in the center, and if you do this, right? In this graph, if you remove any of the edge, it ends up dividing the graph into two parts, and hence every edge, this edge, this edge, this edge, all the edges are actually critical connections. So I hope that makes the concept of critical connection extremely clear. Now let's jump into the brute force way of solving this problem. So let me just remove this. Okay, so let's look at this particular example, for instance, and to explain the problem in a better way, what I will do is I will take a slightly modified version of this graph, and I'll just add one more node to it and one more edge to it, which is 3 to 4. So basically now, if you see, your n is going to be 5. In the sample input given was 4, but then I have added one more node, so n is equals to 5, and your connections array, it is an array of edges basically. It is going to be 0, 1, 0, 2, then 1, 2, and then you have 1, 3, and one more extra edge which I have added is between 3 and 4 basically, right? Now let's keep looking at this particular example. Let's figure out how do we find the critical connections by brute force. Now, so the problem statement says that we have to find such connections. If we remove those connections, the condition is if we remove those connections, that should divide the graph in 2 parts, right? Simply filter the edges on the basis of this condition. So what we can simply do is just iterate over this array of connections and assume each connection is removed. So, when I'm iterating on this array and I'm looking at this particular connection, what I do, I assume that this connection is removed from the system. Now, if this connection is removed from the system, I just need to count the number of parts, exist in the system after this edge is removed. How do I do that? There is something called as depth first search, which is the DFS. So I can traverse the graph using DFS and figure out how many nodes are reachable. So I can figure out reachable nodes. So if you're not familiar with DFS, I will probably make another video and explain what depth first search is, or you can look at other videos also on YouTube available which can explain depth first search. I'll put the link in the description in case I make a video on DFS. The DFS search starts from any of these nodes. So, so to give an example, suppose I remove this edge. So if I remove this edge, what happens to my graph? My graph starts to look like this, So this edge is gone, basically, right? Now I could be starting my DFS traversal from any of these nodes. I can start from here, 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 or here, right? Just for sake of simplicity, let's assume we start from here. And when we try and do the DFS traverse, we will be able to traverse all the nodes, basically. And once we are able to traverse all the node and we know what is the total number of node count, we immediately know that we are able to traverse all the nodes starting from any of these nodes, and hence my graph is actually connected. And if my graph is connected and there are no two parts in the graph, basically my graph is not broken, and hence this edge is not a critical connection, right? And I just repeat this operation for this edge and this edge and this edge and so on, right? And when you repeat the operation, you'll figure out this is not a critical connection, this is not a critical connection. Let's look at this one. So once I've removed this edge, suppose I assume that this edge is removed, right? So suppose I remove this edge. Now what will happen is, let me put this edge back. What will happen is that when you do the DFS traversal, you will be able to do the DFS traversal either from any of these nodes or any of these nodes, right? Suppose you do the DFS traversal from any of these nodes, you will see that you can only reach 3 and 4. So you will be able to reach 3 and 4, and 0, 1, 2 will not be reachable. And you know the total number of nodes are 5, and you're only able to reach 2 nodes. That means your graph is actually broken into 2 parts, right? Or the other condition would be that you probably start with any of these nodes. In that case, you will be able to traverse only 0, 1, and 2, and 3 or 4 you will not be able to traverse, and hence you know that your graph is broken into 2 parts. Hence, that proves that this is a critical connection. Similarly, let's look at this particular example also, right? So let me put this edge back and let me remove this edge. The same story is going to happen over here also. When you assume that this edge is gone and you start throwing a DFS traversal, if you start with node 4, then you will only be able to reach node 4 and rest of the nodes will not be reachable, and hence you know this is a critical connection. Or your DFS traversal will start from any of these nodes, and that is you will be able to reach 0, 1, 2, and 3. And you know total nodes are 5, and you're only able to reach 4. That means your graph must be broken into 2 parts, and hence this is also a critical connection. So I hope that clears up the brute force way of solving this problem. Okay, now let's look at the optimal way of solving this problem. But before we look at the optimal way of solving this problem, I forgot to mention the time complexity. So the time complexity of this algorithm, right, can be calculated on the basis of the time complexity of DFS. So a DFS traversal time complexity is order of V plus E, right? And how many times you're doing this DFS traversal? For every edge, you're doing it once. So you can just multiply it by edge. So this is the time complexity of this algorithm, which you can see it's going to be almost order of VE plus E square, right? And that's like a order n square kind of algorithm, basically. Now, the optimal way of solving this problem is going to be an order n solution, basically. So let's look at how we are going to achieve an order n solution. So to be able to solve this problem in order n, we use something called as a Tarjans algorithm. So now Tarjans algorithm, is a sufficiently complex algorithm, and no interview should expect you to come up with something like this in an interview. But then it is always good to know these algorithms and the thought process behind them, so that you can develop a way of thinking which can help you solve graph problems. So before I jump into a Tarjan's algorithm, let me just explain a couple of terms. So the first term is strongly connected component, and the second term is DFS. So DFS we already talked about. It's a depth first search. What is a strongly connected component? Whenever in a graph, if you pick any pair of nodes, and they are reachable. So node, if you pick A and B node and they are reachable, you can reach from A to B and you can also reach from B to A. And why I'm talking about A to B and B to A, because Tarjan's algorithm works for directed graph as well. You know, so it works for directed as well as undirected graphs. So any pair of nodes, if you pick any pair of nodes and they are reachable from A to B and B to A in a given graph, that means, or in a given in a sub part of the graph, that sub part is called a strongly connected component. Okay, so that is the definition of strongly connected component, and Tarjan's algorithm was built to find all strongly connected components given a graph. You know, okay. Now, having said that, let me just tell you how I'm going to approach this. Because Tarjan's algorithm is a complex algorithm to explain, I will do it in two parts. So part one, I will talk about I will explain the working of Tarjan's algorithm. So I'll explain the working, and part two, I'm going to explain the thought process. Okay, so let's first look at the working of a Tarjan's algorithm. Let me rub this, right? So what I'm going to do is to be able to explain the working of Tarjan's algorithm, right? Let me just quickly rub this and start with a graph which makes it easier to explain the working of Tarjan's algorithm. So I'm going to pick a graph like this. So if you look at this graph, right? If you look at this graph, you see removing this particular edge does not divide the graph in two parts, because anybody can traverse via node 2, and removing this edge also does not disconnect the graph, does not disconnect the graph, and similarly for all these edges. But this edge is a very important edge. You remove this edge and suddenly your graph is divided into two parts, right? So this is the critical edge. Now let's see how Tarjan's algorithm works, right? So Tarjan's algorithm uses DFS to traverse the graph, right? First thing to note. The second thing, for every node, so how does DFS works? You start with a node and you traverse to the next available node, which is directly connected. And once you reach this node, you traverse to the next available node, either this one or this one. And once you are done exploring all the nodes, like for instance, if you go from here to here, here to here, and this node does not have any new nodes to explore because these two nodes are already explored, that means you traverse back basically and your recursion completes. So it's a recursive algorithm, it recursion completes and it comes back. At this point in time, you still have a path to explore, and hence you go on this path and so on. Basically, that's how DFS works. So DFS, nodes are discovered, So you start with node 0, then you discover node 1, and then you discover node 2, then you come back, then you don't discover node 3, and so on basically. So nodes are discovered. That is one thing to know. And the second, so what all things, while Tarjan's algorithm is trying to traverse the graph via DFS, it remembers, what it does is that every time a node gets discovered, it assigns an ID to it. So remember two things it does. First thing it does is that it assigns an ID on the basis of the order it was discovered. So the first node is assigned an ID of 0. The second node is assigned an ID of 1. The third node is assigned an ID of 2, and so on basically. And the second thing it tries to keep track of, let's call it low, right? But what it essentially is, this is the lowest ID reachable from that node. Right? Lowest ID reachable from that node. Now, so let me just write it down. Lowest ID reachable. Right? Now, this is what it tries to track for every node it traverses. Right? So these are the two things. Now, the best way to explain this will be via example. So let me just remove this and let's try and traverse through this graph and track these two items. Okay? So suppose my DFS starts from this particular node, right? So if my DFS starts from this particular node, this node just got discovered. I don't know about the rest of the graph. So what I do is I immediately assign 0 ID to it. And because I know only about this node, what is the lowest node reachable from this node? That is going to be itself. So you immediately assign 0 to it. So these are the two values which I'm tracking for every node. Okay. Now I go from here to here, say for instance. immediately assign an ID to it. And what is the lowest node which is reachable from this node? Remember, the only condition is that you are not allowed to travel back, right? So you cannot look at this side, but you can look at other sides. But the thing is that other sides are not visible to you right now because you've just discovered this node. So the lowest node which is reachable from this node is itself again, basically. So 1, 1. So typically that's how it works. Once you discover a node, you immediately assign the same values to both the discover ID as well as the lowest node. So now suppose you you traverse from here to here. So immediately assign 2, 2. Now once you have traversed here, you start exploring. So when you say, hey, now I want to explore further, you see that this guy can actually reach node 0. So that means the lowest node this guy can reach is not 2 but 0. At that point in time, you change this lowest value to 0. And now you don't have anything further to explore in node 2. So your recursion comes back, you come back here. And again, now once you come back, you compare these low values, the 1 and 0. So what this means is that if 2 can reach 0, that means, and 1 is connected to 2, that means 1 can also reach 0 via 2, without looking back, remember. So it can reach via 2. So in that case, the lowest node reachable is 0 here. And at this point in time, you have explored this side. You came from this side, so you have another path to explore. So now you jump to this particular node. Because this is just discovered and the ID you have to assign is 0, 1, 2 is already gone. So you have to assign 3. And the lowest node reachable from 3 will be 3 itself, basically, without going back, right? Now, once you have discovered this node, what you do is you discover further, right? So you go and discover 4, say for instance. So you immediately assign 4 and lowest node reachable from 4 will be 4 without going back. At this point in time, when you start exploring 4, you go to 5. So, this is 5, 5, right? And once you have explored this node and you see that now this node can actually reach number 3, 5 is directly connected to number 3. So you update the low value. So you update the low value to 3. And when now no further exploration is possible over here, so you traverse back. When you traverse back, you compare the low values. Remember, when your recursion comes back, you compare the low values. 3 and 4, which is smaller? 3 is smaller. That means if 5 can reach 3, 4 can also reach 3 via 5. So the lowest node reachable from 4 becomes 3, right? And at this point in time, you further traverse back. So when you traverse back, what you do is you again compare the low values. The low values remain the same, and hence, no need to update them basically. At this point in time, your discovery or a traversal of 3 has completed, and now your recursion comes back. So now this is the important point, right? When you jump from 3 to 1, going back, right, in your recursion, you compare the low values again. Your same algorithm follows, right? Now 0, 3. When you compare these two, 0 is already smaller, right? This is the most important. This is the point you have to be very careful. Once you traverse back and you see that the low value of this node where you come back after recursion completion, the low values are already lower than from the place you're coming back. That means, there is a gap in the low number, and that means this this edge is a critical connection, right? I will explain the thought process why this is so. But this is what the Tarjan's algorithm says, that once you traverse back and there is a gap in the low values after you have checked them and updated them. So here you have already checked them, 0 and 3. When you compare, this is smaller and you have not updated it, right? At this point in time, this edge becomes a critical connection. See, this edge is not a critical connection because the low values were same after updating. This edge is also not a critical connection. This edge is also not a critical connection because the low values are same basically. Here the low values differ, and hence this is a critical connection. When your traverse has completed and you come back, again you can compare, right? The low values are same, and hence this is not a critical connection. And hence once your traversal completes, you figured out that this edge was a critical connection. So remember 2 points. One, an ID, which is the discovery ID, and the second thing is low, the lowest ID reachable from that node. To begin with, whenever you just discover a node, the low ID becomes its own ID, and then once you traverse further, you figure out which is a better low ID, and then when you come back, when your recursion comes back, at that point in time, you keep comparing the low IDs and keep updating them, right? And that is the algorithm. And the third thing is that whenever When you have finished comparison, at that point in time, you figure out there is a difference in the low ID, and you immediately mark that edge as a critical connection. Now, before jumping into the thought process, let me just quickly tell you the time complexity. The time complexity of this algorithm is going to be order of v plus e, because you are doing the DFS traversal and only once, and that's it. A DFS traversal time complexity is order v plus e, right? Now comes the important point. What is the thought process, right? So the thought process in Tarjan's algorithm is, to explain the thought process. Let me just tell you. Let me just show you something. Suppose I give you a graph like this, right? If I give you a graph like this, can you tell me which edge is a critical connection? Just remove any of these edge. Is it a critical connection? No. Is this edge a critical connection? No. This one? No. This one? No. So basically what we figure out is that if there is a cycle in a graph, that graph does not have any critical connections. Now, let me just give you another example. Suppose the graph is like this. No cycle, right? Now tell me if there is any edge which is a critical connection. Remove this edge. It divides the graph into two parts, one part and second part, right? Remove this edge. Similarly, it divides the graph into two parts. So what we understood is, without a cycle, no cycle, every edge becomes a critical connection. With a cycle, none of the edge become a critical connection. And that is the primary thought behind Tarjan's algorithm. So now, to explain that, let me quickly tell you how, basically. So remember, the algorithm says that to be able to figure out cycles in the algorithm, right? What it does is let's take an example, right? Let's take this graph. So remember, so for simplicity's sake, let me assume that the IDs are A, B, C, and D. So these are not IDs; these are the identifiers of the nodes, right? So what Tarjan algorithm says: do a DFS traversal and keep assigning ID as you discover the nodes. So suppose your discovery starts from here, you're going to assign 0, 1, 2, 3. This is how the IDs are going to get assigned. And what will be the low numbers, the second value tracked? You can assume that to begin with, it will be like this, right? But once your recursion has started here, and remember, this recursion is going to go one after the other, and this 3 will be the last node to get discovered. When this node figures out that it is connected to an already discovered node, because its ID is already lower than the ID of itself, that is when we have found a cycle. And once it has found the cycle, it updates its lowest value to the lowest node reachable. And that low number propagates while you're coming back. So this becomes 1, this becomes 1. And so in a loop, the low values will be the lowest number in the loop itself. So if there is a loop in a graph, the low value will become the lowest node involved in that loop. You can see over here, there was a loop over here of 3, 4, and 5 nodes, and the low value became 3, 3, 3. If you can look at this one, there's a loop in here, and the low value became 0, 0, 0, right? And that is what Tarjan's algorithm is trying to track. And so, and why? So I talked about, right? Whenever there is a gap in the low value, you immediately mark an edge as a critical connection, and that is what this logic says. That if the low values are different, that means these nodes are part of different loops, and hence, if they are part of different loops, this edge becomes a critical connection. So that is the thought process behind Tarjan's algorithm. And here you can see what will happen is, let's walk through this, right? Because I've drawn this graph, let me just walk you through exactly how it's going to. So the first thing, this gets discovered, 0, and the 0 becomes the low value. Then this gets discovered, 1, and 1 becomes the low value. And suppose this gets discovered, so 2, 2 becomes the low value. Then this gets discovered, 3, 3 becomes the low value. At this point in time, you figure out that D is connected to B. So the minimum ID it can reach is 1. So you update this to 1. then you traverse back, you update this to 1, and because you know that there is no gap in the low values, you do not mark this edge as a critical connection, you do not mark this as a critical connection, you traverse back, no difference in low values, you do not mark this as a critical connection, and once you traverse back here, you see 0 is already lower than 1, so you don't replace 0 over here, and hence, and now you see there is a gap in the low values, and hence you mark this as a critical connection, and that is the thought behind Tarjan's algorithm. And time complexity, I already told you that it is going to be order v plus e, and let's quickly run through Tarjan's algorithm on the given problem, and one last time, so that it's extremely clear that how we will use Tarjan's algorithm to solve this particular problem. So what you have been given is this graph: 1, 2, 0, and 3. Right now, what will happen is that you can start the discovery from any node possible. So to make it slightly more interesting, let me start the traversal, say this node possible, right? So suppose I start the traversal from this node, right? This becomes the ID 0, and the lowest node reachable is 0, right? When you traverse from here to, say, let's traverse on the other side basically. So you traverse from here to here, the ID becomes 1, 1. So the ID 1 and the lowest value reachable is 1. Then you, from here, without going back, you traverse on this side, and the ID of this guy becomes 2, 2. And at this point in time, let's traverse on this side basically. So when you traverse from here to here, this becomes the fourth node to be discovered. So ID becomes 3, and the lowest node reachable right now is 3 itself. Now, without going back, this node, what is the lowest node it can reach? It is still itself basically. So nothing to update any further. So once you have explored node 3, once you know that there is no more edges to explore node 3, at that point in time, your recursion starts to go back. And because 3 still can reach itself as the lowest node, and once you go back, you compare the low values 2 and 3. And remember, you always take the lower one. So you take 2, so you don't update this, and 2 becomes the lowest node still reachable from point 1. And because after you have compared, you figure out that there is a jump in the low values, you immediately mark this edge as the critical connection. At this point in time, remember we came from here to here to here, this edge was still unexplored, right? So what happens is that when we are at this node, we explore this edge. And at this point in time, you figure out that this node is actually reachable. It can reach at ID 0. So remember, this value doesn't matter. We can reach ID 0. So what we do at this point in time, update the low value to 0, right? And now, once you have explored this particular edge, and you know this is already explored node, then that's when your recursion goes back. So now, once you go back, you again compare the low values, 0 with 1. You figure out that 0 is smaller, so you update the low value to be 0 over here, and then from here you go back here. And then at this point in time, your low values remain the same. And because there was no jump in low values, 0, 0, 0, so none of these edges become critical connection, and hence your Tarjan's algorithm is completed, and only one edge was found as the critical connection. I hope that clears up the Tarjan's algorithm and the optimal way of finding critical connections in a network. This is a fairly complex algorithm to understand, but once you see the picture, once you see the reasoning behind it, then it is extremely clear. Yeah, thank you.